we're going to do something different. It basically builds up from derivatives. Here, let's do this. This is a new chapter. It's called integrals, okay? So what is it? It's the opposite. It's the opposite of a derivative. It's working backwards, basically, that's what it is. For example, if you have y equals x squared, yeah? Y prime is 2x, right? We've been doing this for a few weeks. So this is called the derivatives. But what if you want to go backwards? What if they give you y prime and they ask you what is y? That's where the integral comes into play, okay? It works like this. We're gonna start off pretty easy, right? For a polynomial. So the derivative of a polynomial, if it's in this form, some constant a times x to the power of k, y prime becomes a times k times x to the power of k minus 1, right? This is the derivative. What if you want to work backwards though? So this is called the integral. What's the formula? It's not really a formula, but this is the notation. This is what's going to help us do these. So when you're doing an integral, let's say you have y prime is now some number a times x to the power of k, yeah? This is our integral. So what is going to be our original function? What you do is you're going to add 1 to the exponent. Instead of subtracting 1, you add 1. And instead of multiplying by k, you would divide by k. There you go. That's the difference. Let's do a quick question here. For example, if y prime is 4x squared, right? 4x squared. Then look at this. Y is going to be, you're going to add 1 to the exponent. So it's going to become 4x cubed. And then you're going to divide this by a 3, like that. This is for polynomials. The rules are going to change, but this is like the basic power rule for polynomials. The rules are going to change when we get a new function that's not a polynomial. Here, we can show this as well, like what's going on here, proof. We can show that this is true. Let's say we start off with y, right? Y is 4 over 3x cubed. What will be the derivative of this? How do you find y prime if this is your y?
You bring the 3 to the front.
Yeah, you bring the 3 to the front and then you subtract 1. Right, and look at this, 3 and 3 cancels out, you end up with 4x squared. So this is the derivative. But the integral is the other way around. A quick note, whenever you integrate something, like we do here, it is common knowledge that you add plus c at the end to this. It's not common knowledge, but that's the notation. It's because you see 4 over 3x cubed. If I had a 4 over 3x cubed plus 9, the derivative, because the 9 is going to disappear, it still would be 4x squared. If I had a 4x cubed plus a pi, it'll still be 4x squared. So this constant here can be anything, okay? So we denote that with a plus c. So you add a plus c at the end because there could be a constant attached to this. But this is the formula. Add 1 to the exponent, and whatever the old exponent was, divide that. Cool? And this is the notation for an integral. See this? Kind of looks like an S. What is exactly an integral? We know the derivative means it's the slope, right? Derivative at a certain point means it's the slope of the tangent line at that point. But what in the world is an integral? Integral is this. Let's say you have some function that looks like this. Well, this is called an indefinite integral. That means we don't know where its bounds are. We're going to see later that it'll be bounded from a certain x value to another x value. But this is indefinite. We don't know where it's bounded. But what an integral gives you is the area underneath the curve. Derivative gives you the slope of the tangent line, right? Integral gives you the area underneath a curve. So 12x cubed. Again, this is the formula. If you have a times x to the power of k, the integral becomes a times x. I don't know if I wrote it right last time, but it's +1 like this. And then you also do a +1 on the bottom. So using this, if this is y prime, right, what will be y? A stays as it is. x3 becomes x4, right?
And you divide 12 by 4.
And then you divide by 4. So this is going to become 3x4. And we can check. We can always, that's the beauty of this. You can always double check. When you go backwards, when you find the derivative of this, you should end up with this. And again, you need to add a plus c element to this. So if you find y prime, it's going to be what? 12x3, and that's what we started off as. And the c here is a constant for which the derivative would be a 0. Cool?
Mm-hmm.
It's going to get more and more difficult, but that's the idea. This one, it looks weird, but it's the exact same thing. If we can somehow write it in this form, right? When we know we can, you can just use this formula. It's not in the right form right now. By the right form, I mean, let's take the denominator into the numerator. What do we get? If we throw this up top, you can throw them up and down, right? If you throw them up and down, the sign of the exponent is going to change. So if you throw t4 upstairs, what do you get? T?
-4.
-4. So there you go. That's our notation. Now let's use this formula. What do they call this? They don't call it y or anything, but it doesn't matter. So this is y prime. This has already been derived. Now we're working backwards to find the original. Again, look at this. A becomes a, nothing changes. T, you need to add a 1 to this. So this is going to become -3, and you divide the entire thing by -3. And that's all, and you're done. Cool?
Mm-hmm.
So again, just follow this, right? It's the exact opposite of a derivative. But integrals have way more applications than derivatives. We'll see it later. Derivatives is usually just for the rate of change, whereas integral is, there's a lot more applications of it. This one is tricky. I'm not gonna lie to you. This one, it's because, again, this is the formula. A times x to the power of k, when you find the integral, becomes a times x to the power of k plus 1 over k plus 1. Using this was how to, let's first rewrite this. If you rewrite it, by rewrite, I mean throw the x up top, what do you get?
X to the power of -1.
X to the power -1 dx, yeah? This is just the notation. Whenever you see this line, this is called the integral. It has to be attached to some something called d something, depending on the variable. This means this function here has already been derived in terms of x, okay? That's what that means.
Mm-hmm.
Now think about this. Use the formula here. You're gonna get a very interesting result. Use this formula, what do you get as the integral? Two is gonna stay as 2, right? What about the x? How many x's do we have now?
0.
0. What do we get on the bottom? So -1, right? This is our k right now.
You get a 1.
No, you get a 0. Right? -1 plus 1. See k plus 1?
Mm-hmm.
K is -1. But we know mathematically this is impossible. So how does this even work? Turns out you cannot use the power rule for this case. Because if you use the power rule, you're going to get a 0 in the denominator, right? So you can't use a power rule. So what do you do for this one? It's a simple formula. If there's an x power 1 on the bottom, when you integrate it, it's going to become 2 times the natural log of x. So it becomes 2 ln x plus c. Remember when we were trying to derive something like 3 to the power of x, this became 3 to the power of x times ln 3, right?
Mm-hmm.
Kind of like that. It's similar to this. If there's an x power 1 on the bottom, it's going to become a ln of x. Okay? This is a new rule now. If you have anything to the power of x, this becomes a ln x. And that's it for that question. X power 1, the power rule doesn't work. This one, it's going to work because as long as you can write it in terms of a power like we did with derivatives, it's going to work. You can rewrite this as x to the power of 1 over 2 dx, right? This is your y prime. Now, if you use a formula, what do you get as your integral? This one, it works. It's just the normal rules.
You get x to the power of -1 over 2.
Okay, so now we're working backwards, yeah? Yeah, if you were to find the derivative, it would be 1 over 2 x to the power of -1 over 2. This is the derivative using the power rule, but now we're working backwards. You need to add 1 to this. What's 1 over 2 plus 1? It's 1.5, right? Which is 3 over 2. And then you're going to divide this by this new exponent, 3 over 2 plus c. That's it. Again, we're just using this formula right here. Add 1 to the exponent, and whatever that new exponent is, you're going to divide it by that exponent as well. All right, this one is tricky. Well, this is just normal maths, but you see how there's 3 levels here? The first level, the second level, the third level. Where does the 2 go? Does it go to the second level or does it go to the third level? Or sorry, does it go to the second level here or does it go to the first level? Because we can simplify this a little bit.
The first level.
Okay, we can prove that. So this is the same thing as x to the power 3 over 2 divided by 3 over 2, right? And you can change that into times 2 over 3. Yeah, so that's right. It's going to go to the top. I messed up the notation here. So it's going to be 2 x to the power of 3 over 2. Look at this. This 2 is your square root, and then x cubed, and then you have a 3 down here plus c. And that's a little bit cleaner. Okay, and that will be the final step. You can't go further from this. Cool? Again, we're just using this formula. The only exception was when you have a x power 1 on the bottom, it's going to become a ln of x. So far, most of these have been like a one-step question. But like we saw with the derivatives, there is a chain rule component that's going to come into play. Not yet. Chain rule only comes into play when you have a function within a function. When something is a combination of two different things. Here you can see this is just a power 4 polynomial. This is just a quadratic polynomial. We don't have any chain rule shenanigans just yet. All right, again, if there's a plus, like we did with derivatives, you just do them individually. Okay, you just do them individually. Or you're going to use the same formula here. This is going to become, you add a 1 to the exponent, and whatever the new exponent is, you're going to divide it by that. So tell me, what does the first term become? 5u4.
5u to the power of 5.
Yeah, what do you divide this by?
5.
5. What about the next one?
9u to the power of 3. And then you divide it by 3.
Right, and then a plus c, and let's see if we can clean this up a bit. 5 and 5 cancels out. You get u5. 3 goes into 9 3 times, plus 3u cubed, plus c, and you're done. And you can quickly check as well, right? The derivative of u5, well, the 5 comes down and you take away 1, you get 5u4, which is what we have here. What's the derivative of 3u cubed?
9u to the power of 2.
Right, exactly. So you see, you can check really quickly, yeah? So that's the beauty of integrals. You can check it, and that is what it is. That's not what they got. Yeah, they didn't write the plus c thing here. Oh, they did, but I don't know why they didn't write it here. Whatever. Let's look at this. Again, as you can see, it's pretty easy. Okay, there's nothing tricky going on. No one's trying to trick you. Look at this. This is very quick. You're gonna add 1 to the exponent, becomes a 7. You're gonna divide this by 7 as well, plus c. And you clean this up. 7 goes into 35 5 times. 1 and done. This one, you first rewrite it by bringing t8 to the top. It's gonna become t negative 8. What's the derivative of this? Not the derivative, sorry, the integral. Again, the sign determines what we want, what they want us to do. If you see this s, squiggly looking s sign, it's the integral. What would it be for question 2 here? Again, look at this one, because it's in the right form.
Negative 9t to the power of negative 7.
Okay, yeah, I think you're right. But it's not negative 9. You're gonna add 1 to this, so it's gonna become negative 7, and then you're gonna actually, you're right. It is negative 9. You're a step ahead. Yeah, that's good. What about 3? For 3, you need to know what 1 plus 2 over 3 is. See 1 plus 2 over 3? You can, if you have a 1, you can just combine it as a mixed fraction like that. It's 5 over 3. Or alternatively, you can take the common denominator, which is 3. So you need to multiply this by 3 on the bottom. On the top, you get 3 plus 2 over 3, 5 over 3. And then you divide this by 5 over 3. Where does the 3 go? To the top level or the second level?
The top level.
Yeah, the top level. So there's a 3 here, and 5 goes into 15 3 times. So the final answer will be 9x 5 over 3 plus c, and you're done. Cool?
Mm-hmm.
Easy peasy. There's this last one again. It's going to be 48u negative 4 over negative 4. So that will be 12, negative 12u negative 4 plus c. That's it. Actually, all these are interesting. Look at 5. What's the integral of that? Again, you add.
To the power of 2 over 2.
Yeah, that's it. This is not in the right form. Let's change this. And understand what happened. This is x to the power of 1 over 2. We're going to throw it upstairs, right? It's going to change the exponent. This is going to change the sign. It's going to become negative 1 over 2. Okay, what's the integral?
One over 2x to the power of 1 over 2.
X to the power of 1 over 2. It's going to be 2x to the power of 1 over 2. Because you need to divide x to the power of 1 over 2 by 1 over 2. And we've seen this a few times. The 2 is going to go all the way top. And that's it for that, plus c. Plus c. 7 is interesting. I'll give you a hint for 7. You can rewrite this, again, you look at your variable, it's u. So you can rewrite this as 4u to the power of 0. And the same power rule applies. What do you get?
4u to the power of 1 over 1.
Yeah, and that makes sense, right? Because the derivative of 4u is 4, because the letter disappears. And that's it for that question. All of these are like pretty, it's usually 1 steps. Look at this, we're gonna throw it up top. This is 8x to the negative 1 over 3, the integral with respect to x. What's negative 1 over 3 plus 1? Negative 1 over 3 plus 1. You can think about it this way, right? Look at this. There's a 0 here. We can make increments of 1/3. This will be 2/3. This will be 3/3, which is a 1. So every box here represents 1 over 3. We have negative 1 over 3 here. Yeah. We're trying to add 1 to this. That means we're trying to add, again, there's so many ways to do this. This is like the visual way. If you're adding 1 to negative 1 over 3, you're going to the right by 3 boxes. See, 1 box here, 2 box here, 3 box there. You get x to the power of 2 over 3. Divide this by 2 over 3 as well, plus c. And we know this 3 is going to go all the way to the top. And so you get 24 over 2, which is 12, x 2 over 3 plus c as your answer. Cool?
Mm-hmm.
Does this make sense or no?
It does.
This one, look at this, very simple. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by new exponent. Add 1 to the exponent, because this is 4x 0 right now. Add 1, it becomes 1 over 1, like that. And you're done. Things are gonna get a little bit more interesting. Actually, let's see if you remember this one. I can rewrite this for you if you want. So right now we have this. What will be the integral of this guy? Any ideas?
For the first one, you get u to the power of negative 1 over negative 1.
Yeah. What about the second one?
You get 4u to the power of 0 over 0.
Yeah, but see, that's the trick. You cannot have a 0 in the denominator. So there was a new rule for this one.
You use ln.
Yeah, specifically when you have power 1 in the denominator, right? Doesn't matter. The variable is redundant. You can call this z. It doesn't matter, right? X, Z, K, it doesn't matter. As long as it's a variable. So it's going to become ln of u. Okay, like that. And you're done. So when you have a power 1 in the denominator, it's going to become ln. Here we can quickly do this one as well. Again, it looks weird, but it's not that difficult. Because I'm going to first rewrite it in this form. If I throw this up top, what's going to be its exponent? I throw the root t, it's on the bottom right now. If I throw a top, what do I get?
T to the power of 1 over 2.
So that is what we have right now, okay, for this. We need to throw this up top so that we can use the power rule. It's going to become negative 1 over 2, right?
Mm-hmm.
Numerator, denominator, if you swap positions, if you throw it up or down, the sign is going to change here. I can do 20 of these. 2 negative 2 becomes 1 over 2 positive 2. 1 over 2, this becomes 2 negative 2. Well, this is actually the same thing. But if you have something like 2 negative 2, this is going to become 2 positive 2 if you throw it up top. So the only thing that changes is the sign of the exponent when you swap positions up and down. And from here, it's simple, right? You're going to add 1 to the exponent. What's half plus 1? 3 over 2. Okay. And then you're going to divide this by 3 over 2. The 2 is going to go up top here. What's negative half plus 1? You can think about it this way as well. Negative half means negative 0.5. You add this with 1, you get positive 0.5, which is 1 over 2. Yeah?
Mm-hmm.
And that's it. Again, this 2 is going to go up top. It's basically a one-step answer. Here we just rewrote it to see what the exponent was, but you can skip this step if you're comfortable with visualizing that root just means to the power of 1 over 2. This book is a little bit weird in the fact that it's not weird actually. This is a really good dumb book because you can actually just write it. If you had this book, you can literally just write the answer right there, you see? Usually with textbooks, they don't give you any space to write your answers. But this one, they give you space and the answers just follow the sections as well. So you can double check really quickly. We don't have to worry about that. But if you were to do this on your own, then that's good. All right, so the next one is called definite. What does definite integral mean? It means there's gonna be a bound. There's gonna be a lower bound and an upper bound. So let me show you a quick example. Let's say we wanna find the area underneath y equals x, right? See this? Looks
Mm-hmm.
like this, right? Let's say we want to go from 0 to 4 on the x. We're going to do this the dumb way, and I'm going to show you how to do this using integrals because we have formulas for, again, this is a triangle. This is a pretty simple one. But usually we don't have nice shapes in real life. We're never going to get something perfect. We're going to get something weird like this. And it's very difficult to, you know, find the area using the normal methods, which is for a triangle, it's base times height over 2. Anyways, if the x value is 4, this is your function. What's your y value at this point? This line is y equals x. When the x value is 4, what's the y value?
4.
4. What's the area of this triangle?
16.
16 over 2, right? Base times height over 2. Base is 4, height is 4.
Mhm.
So it'll be 8. Yeah?
Uh-huh.
This is doing it by traditional means. We can prove that this is the case. So let's say our y prime is our function x dx. Okay. And now we have a bound. We have a lower bound, which is 0. We have an upper bound that is 4. Again, forget about the 0 to 4. What's the integral of x? You can use the power rule, right? You add 1 to the exponent, and then you divide it by the new exponent.
X to the power of 2 over 2.
X to the power of 2 over 2. Now, usually we add a plus c, but that's if the bounds are undetermined. Here they have given us bounds. There's a lower bound and an upper bound. You don't add the plus c because this will give us an exact answer. There's no plus c attached to this. And then what you do is you write a line like this, then you write your bounds here, 0 to 4. Now, what does that mean? It means this. Let's say you have some function a to b of f of x, or f prime of x. The answer to this is f of b, again, you've integrated this function, minus f of a. This is going to be a new formula now for, this is called a definite integral, because we are aware of what the bounds are. So for us, f prime of x was x. F, after you integrate this, it becomes x squared over 2, okay? And look at this, you're going to plug 4 in there. So this becomes 4 squared over 2. That's f of b. Again, it's a and b. F of b minus f of a will be, you plug 0 in there as x. 0 squared over 2. You get 16 over 2 minus 0. And see, you get an 8 as well, which is what we had here. So you can find the same thing using integrals. And it's best for curves. Let me be honest with you. Because for straight lines and whatnot, you can turn it into like a parallelogram, a triangle, rectangle, whatever. It's simple, right? But this one, you can't turn a curve like something like, what's the area underneath? You see something like this. What's the area here? You can't be precise. Even if you were to convert these into a bunch of triangles, you'll never be exactly precise because you'll have some space left over there. What calculus does, what integral does, is that it converts it, this is gonna sound weird, it converts it into infinitely many triangles. Very small, not triangles, or rectangles. See these? It basically converts the area underneath the graph into infinitely many rectangles, and it adds up all the areas of the rectangles. And because there's an infinite number of them, there's no like open space like it would be with a triangle or something. Okay, because there's an infinite number of them. That's the logic behind it, but no one's going to add infinite number of rectangles by hand. That's why you use this. This is literally what we're doing here. We've converted the area underneath the curve into infinitely very thin rectangles. We found all the areas of those rectangles and we added them up. Okay, that's the logic. So definite integrals, there's not going to be any plus c element. And once you actually find the integral like we did here, you're going to put the upper bound in here as x, minus you're going to put the lower bound in there as x. And this, whatever this gives you, 8, the final answer, is the area underneath that curve. Or a straight line, it doesn't matter, it's the area. This is the way they have written it. Basically, g of x is the integral of f of x, okay? We use f prime of x, and then this became f of x. It's the same idea. Once you integrate this, you're going to put the upper bound, you're going to put the lower bound, you're going to subtract it. You'll see it's pretty simple. It's not that difficult. It's just one extra step from everything we've done. All right, our function is 9x squared. What's the integral of 9x squared? It's the power function. Use the power rule.
Three x to the power of 3.
Yeah, 3x to the power of 3. But because this is a definite integral, how do we know that? It's because they've given us a lower bound and an upper bound. We're going to write this line, straight line, 1 and 2. In the next step, we're going to plug the upper bound in there, minus plug the lower bound in there as x. That. So you have 8 times 3, 24, minus 3 times 1, 3. So the answer is 1. Cool? What does that mean visually? 9x squared is a parabola, right? That goes through the origin like this. Let's say this is the graph of y equals 9x squared. What we found was the area underneath the curve when the x value is 1 till when the x value is 2. You see this area? This is 21. Okay?
Okay.
This is 1 over x squared. This one looks weird. Can x be 0? 1 over x squared. Can x be 0?
No.
No, right? That means there's an asymptote here. The curve will never cross this asymptote. And it's because the denominator has a higher degree than the numerator. There's also an asymptote here. I'm just trying to graph this. So it must look like and then this will never be negative either, right? Because you have a squared on the bottom. The y values will never be negative. It cannot pass through this wall or this wall. The graph of this looks like this. And we're trying to find its area from 4 to 12. So from 4 to some arbitrary 12. This is what we're trying to find. So that's the idea here. It looks like a rectangle there, but it's because this is a rough sketch. It's not going to be a rectangle. It's going to be something like this. Like this, it's going to be. Where it's not really a rectangle. It's a curved shape. It's not like a trapezoid or anything either, because all of those are required to be straight lines. This is not a straight line. That's why this comes into handy. Integrals are another name for integrals is antiderivatives. Okay, integrals, antiderivatives, denoted by this symbol here, the S symbol. They both mean the same thing. It's the area underneath a curve. All right, this one, I'm going to give you a hint. We're going to rewrite this as, again, every single time to use the power rule, you must have your function in the numerator. You need to see what the exponent is. All right, what's going to be the antiderivative of x to the power negative 2?
X to the power of -1 over -1.
Yeah, -1 over -1. So this is the antiderivative or the integral. And then we're going to throw in the upper bound and the lower bound. So I'm going to clean this up actually. Can you tell me what this becomes if you clean this up a bit? Something that we can work with? -1 over x. This -1, I'm going to write it outside. And you see this x to the -1? Toss it in the denominator, it becomes x to the power 1, like that. Next, we're going to plug in the upper bound, so 1 over 12 minus, then we're going to, again, whenever you have a negative sign, put a bracket there, 1 over 4, like that. So you get -1 over 12 plus 1 over 4. Now see, we're back to grade 5. How do you add these fractions?
You find the common denominator.
Which is 12, so multiply this by 3, -1 plus 3 over 12, 2 over 12, the answer is 1 over 6. And that's the area underneath the curve for this function from 4 to 12. Make sense? And that's what they got as well. We're gonna do, You wanna have a crack at this? What's the antiderivative of this?
Wait, when you bring the t up, do you get t to the power of -1 over 2?
Absolutely right, yep.
You get t to the power of 1 over 2 over 1 over 2?
Yes, so t to the power 1 over 2 just means it's the square root of t. Over 1 over 2, we know that the 2 at the very bottom comes up top like that. 9, 4, right? Then you're gonna plug the upper bound. You get 2 root 9 minus 2 root 4. What's the answer? This is like checking your mental maths as well.
It's 2.
Yeah. And you're done. Easy peasy, right? 2 steps. Don't you love questions that are just 2 steps? I'm a big fan of two-step questions. What about this one? Any ideas?
You bring the x to the top.
So again, yeah, you could, right? But then you're going to end up dividing by 0 for this one. Remember, if it's x to the power 1, the integral or the antiderivative is simply ln of that. Okay?
Mm-hmm.
Now ln and e, these are inverse functions. It's very similar to log x and 10 to the power of x. Ln of x and e to the power of x, they're inverse functions. So in the next step, when we plug e as x, you get ln e for the first upper bound, minus the lower bound is ln of 1. Now you can plug this in a calculator if you want. Ln of e is a 1, ln of 1 is a 0. So you get a 1 as your final answer. But ln and e, they cancel each other out. You get a 1. And that's it. Easy peasy. Is this difficult?
No.
What's the purpose of an integral? What does it give? It gives you the area underneath the curve, right? It gives you the area underneath the curve. What does a derivative give?
The slope.
The slope, yeah, slope of the tangent line, whereas integral gives you the area. And that's the difference. Now, usually when you're doing integrals, it's quite hard to deduce what the integral is, especially for something like this one. You see sec theta? Derivatives is easy, right? Derivative sec is simply 1 over cos, and we know the derivative of cos. But when you do the integral, right? When you do the integral, for sec is 1 over cosine, the same rules don't apply. There's no quotient rule for integrals. That's why usually they will give you, initially when you start anyways, like these can get overly complicated, but they usually give you like a formula sheet to go along with it. Because these are not power functions. Now, power functions are like polynomials or anything you can write in terms of x to the power something. If you look at trig functions, which we did yesterday as well, those are not power functions. Those are separate functions. You cannot write sine in terms of sine to the power of x power 1 or something like that. So if you remember from yesterday, sine, the derivative of sine is cos, right?
Mm-hmm.
Now look at this, the integral of cos is sine. It's the opposite. The derivative of cosine was negative sine. Now the integral of sine is negative cosine. Most of these, this looks kind of complicated, but I can tell you most of these are going to be one-step answers. You just need to look at what the formula is. Look at this. We have the integral of cosine theta. What's the integral of cosine theta?
Sine theta.
Yes, sine theta. And our bounds are, upper bound is pi over 2, lower bound is 0. So again, you plug your, again, these are definite integrals, so you don't have to do the plus c. You get sine of pi over 2 minus sine of 0, like that. You can plug this in your calculator if you'd like. Sine of pi over 2 is, you have to be in radians though, because these are not degrees. It is a 1. Sine of 0 is a 0, so the final answer is 1. Make sense?
Mm-hmm.
What does this mean visually? Cosine x looks like this. It's going to start at 1. It's going to go down to -1. Looks something like this. Again, it goes on forever. It's a periodic function. This right here, the x-intercept, is pi over 2. Okay, this graph right now is y equals to cosine theta or cosine x, whatever. What did we just find? Our lower bound was 0, so here. Our upper bound was pi over 2 right there. We just found the area underneath this curve from here to here. So this is the area that we found, right?
Mm-hmm.
And as it turns out, for some magical reason, it's exactly 1. It's pretty cool, right? You'd expect there to be decimals or something like that, because that is not a nice shape. That's like something like this. It's not even like a circle either. Like, I don't even know how to describe it. Something like that. Turns out that area is exactly 1. In other words, if you were to split it into an infinite number of small rectangles, you add the areas of all these rectangles, that covers the whole thing, you're going to get exactly 1. So cosine becomes sine, and then yeah, it's a one-step answer from there. Okay, we're not going to do that. We're going to do these guys. All right, what's the integral of tan? If you look at it here, it's going to become ln, yeah?
Mm-hmm.
This is the absolute value sign, because ln, you can't have a negative number inside it. Ln of sec theta, and you don't have to worry about the plus c because these are definite integrals, 0 and pi over 3. And then you want to plug those into a calculator. Sec of pi over 3 minus ln of sec 0. Whatever that is on a calculator. Cool.
Mm-hmm.
Do you have a calculator on you right now?
Yes.
Okay. Remember this. Secant is cosine flipped upside down, okay? There is no button for secant, cosecant, or like these secondary ratios, which is these 3 of them: cosecant, secant, and cotangent. There's no button on a calculator. So the question is, how do you plug this in? I'm gonna plug it in like this. It's gonna become ln of bracket open 1 divide, because secant is 1 over cosine, like that, minus ln of 1 divided by cosine 0. This is how you'd plug it in.
How do you do ln?
There should be a button called ln. What calculator do you have? Tell me the name up top. The model number or whatever. Does it have a name?
It's like Texas Instruments.
Yeah, what's the model number? XI30A or something. What is it? Top right or top left? Nope, no
The
name.
number is like rubbed off.
The number is what again, sorry?
It's like rubbed off, so I can't see it.
Oh. Does it look anything like this?
Kind of.
Uh, I think you told me once upon a time, but I forgot which one is it. Okay, is it this one?
Yes.
All right, now we're gonna look at this in more detailed. How do you do ln is the question. You see this button right here? Next to the right of off. To the left of off, sorry. LN?
Mm-hmm.
That's it. It's to the button to the left of ln, off. I plugged that in, everything, I got 0.693.
It's giving me error. I don't know why.
I think I know it's because your calculator is it's a little bit weird. You have to type in the numbers first and then type ln second, I believe. It's not like a normal calculator. You have to first type in the number like 2 and then you press ln and then it's gonna give you the value of ln 2. It's okay, don't worry about it. But this is how you'd plug it in using ln. All right, the next one. What's the integral of secant? I mean, as you can see, these are pretty simple, right? Because you have the formula sheet right there. Secant is going to become ln of secant plus tan theta, and we're not interested in the plus c because this is a definite integral. You have negative pi over 6, you have pi over 6. You're going to plug the upper bound first, minus plug the lower bound and subtract them. It's not, right? You understand that? We have the formula right there. Sec becomes that, plug the upper bound, the lower bound. What about this one? Forget about this question. What if I asked you, what's the integral of theta d theta? See this bit here? In other words, you can also look at it as this. What's the integral of x with respect to x? You're going to have to use the power rule.
X squared over 2.
Yeah, x squared over 2. So this becomes theta squared over 2 plus the integral of cosine sine theta, like that. This is the integral. And then you have pi over 3, you have a 0. Next step, you have pi over 3 squared divided by 2 plus sine of pi over 3 minus 0 squared over 2 plus sine of 0. This entire thing is 0 because sine 0 is a 0 and 0 over anything is also a 0. And this is going to be your answer when you plug it into a calculator. Cool? So again, yeah, if you have the formula sheet, these guys are not terribly difficult. I want to leave you with something a little bit more interesting. I'm thinking. Okay, this one maybe. All right. I'll give you a hint for this one. And this is where the chain rule is going to come into play because we have a linear function on the bottom of a, what is this called? Rational function. So this is where the chain rule element comes into play. I'll give you a hint. The integral of 1 over x is ln x. I'll give you another hint. The integral of 1 over 2x is ln of 2x, okay? Ln of 2x, whatever's the bottom, goes inside the ln, but then you have to divide it by 2. This is the derivative of this. If you're in the general form, if you have 1 over f of x, the derivative, sorry, not the derivative, the integral is ln of f of x, but then you need to divide this by the derivative of the bottom. So using this idea, what's the integral of 1 over 3x plus 2? It's going to become ln, yeah?
3x.
Plus 2, the entire thing as it is, ln of fx, ln of fx, over what? What's the derivative of 3x plus 2?
3.
3, right? Plus c, then there you go. Now what's the point of the dividing by 3 at the bottom? It's because that's a chain rule component. When you go to find the derivative of this, you're going to get 1 over 3x plus 2 times 3, okay? But we didn't have a times 3 up here. We had a 1. So we need to get rid of this chain rule component. That's why when you divide it by 3, they cancel out and you get a 1. Cool.
Mm-hmm.
I'm gonna trick you. Well, I'm gonna try to. I don't know if I can. This one's not gonna work, by the way. I was gonna give you 3x squared plus 2, but this is a completely different beast. Let's try another one. Let's try another one simple. All right, maybe this. Okay, there we go. With everything we've learned today, are we able to do this? Yes or no? We learned the power rule. We learned some trig, nothing to do with the trig. We also learned the ln thing. We haven't learned anything about quotient rules or anything like that. Do you think we can do this? The answer is yes, by the way. We're gonna be smart about this. What we're gonna do, and this is what you do also when you're trying to find the derivatives, we're gonna split it up. When you split it up, things become easier. See, like that?
Mm-hmm.
You can split it up, right? Yeah, like this. Now look at this. X and x cancels out. So you have the integral of 2 plus 3 over x. Now I'm going to give you a hint for 2. 2 is the same thing as 2 times x to the power 0. What's the integral of 2x to the power 0? Use the power rule.
2x over 1.
Yeah, 2x over 1 or just 2x. What's the integral of 3 over x? Again, if there's an x power 1, right? It becomes what? You can't throw it up top. Power rule doesn't apply because you'll be dividing by 0.
You use ln.
Yeah, it's going to become 3 ln x. Put an absolute value sign there. Plus c. And that'll be the final answer for the integral of this. Cool?
Mm-hmm.
So this integral function will basically give you the area depending on what the x values are, similar to the derivative. When you find the derivative, it gives you a function. And if you have an x value, you can find the slope of the tangent line at that. Same thing here. This right now is the area function. And if they give us bounds, we can find, because this applies to everywhere for this curve. Let's imagine that this one doesn't look anything like this. Let's say this one looks something like this, right? Anywhere,
Mm-hmm.
the area is given to you by this function. The only difference is what's the upper bound, what's the lower bound. What's the upper bound, what's the lower bound. Okay, anyways, let's call it a day there for today.
Okay, thank you.
See ya.